let's move to the next presentation, which is web-based modeling tools with EMF.cloud, and it will be given by Philipp Langer from Eclipse Source.
Thank you very much. Yeah, I will just start sharing my screen. Desktop 1, so share.
Yeah, we see your screen.
You see it? Okay, perfect. All right. Hi, everyone. My name is Philipp Langer. I work with Eclipse Source in Austria, Vienna. And Eclipse Source is a service and technology provider for open source technologies in the Eclipse ecosystem. And I myself, I'm mostly specialized on web-based domain-specific modeling tools, and also on building domain-specific graphical models. And that's what I want to focus on today. So first of all, I would like to thank Jan for his presentation, because it did a very good groundwork for what we are talking about today, because we are building on top of the technologies that we've just seen. Oh, sorry, I think I accidentally muted myself, sorry. So let's start. Basically, what you all know that in the last, I don't know, 10 or 12 years, the Eclipse modeling framework and the Eclipse Rich Client platform is a very, very nice technology ecosystem that allows us to build domain-specific modeling tools. And with that, I mean tools that not only cover diagrams, but also textual models, table-based UIs, and even form-based UIs. So you see examples of those tools here. However, also as Jan mentioned, in the recent years, more and more the requirements arose that those tools are not only built on top of rich client applications, but also on top of web-based technologies. And there are mainly two reasons for that. Web-based technologies like web-based UIs like HTML5 and CSS and SVG, they offer quite a lot of flexibility in terms of how you can implement user interfaces and make them look very modern and smooth. And also in terms of rendering speed, they have certain advantages in some cases, especially when it comes to SVG, for instance. Also, they sort of detach or they remove the constraints that you have when you integrate that UI in a certain application. Because if they are HTML based, they can be not only integrated in rich client applications like Eclipse or in Visual Studio Code, but also they can be executed in the browser, which means that you can deploy your web application, your applications in the cloud and just access them using a browser without any installation. So those are the reasons why web-based modeling tools also became more and more trendy and also useful. The question now is, of course, how can we still use all the greatness that we mentioned before when building web-based modeling tools, when building modeling tools based on Eclipse and EMF, now when we want to do the same based on web-based technologies like Theia, Chromium, and VSCode. Basically, there are already a couple of technologies that we can actually use to do that today, and Jan also showed already a few of them in his talk. So he covered, for instance, the textual languages that can be just as before used in a web-based context. Also, he has shown Splotty, which is covering a part of the diagram area. And there are also other frameworks like JSON Forms, which can help you to build form-based modeling tools or UIs for modeling tools that can also, in some way or another, hook up with a modeling platform that runs on the server. However, what we would like to achieve with EMF.cloud is to make it more simple to hook up those, I would say, modeling tool front ends to modeling backends that actually run the Eclipse modeling framework, so that there's less effort to build such tools, comparable to how less effort it is, or how few effort it is to build it today in Eclipse Rich Client. Have more standard components around that you can use, and also encode the best practices that you typically apply when building such modeling tools. So that's basically the overall goal of the Eclipse project called EMF.cloud. So really the goal is to provide a common home, sort of like an umbrella for components that facilitate or simplify the usage of EMF and its ecosystem, and help those components to incubate towards becoming standard components that you would use when building such tools, and that encapsulate the best practices, some of which also Jan already mentioned in his previous talk, like the reactive unidirectional active action cycle. So EMF.cloud is currently an Eclipse incubation project. It has been, I think, founded 1.5 years ago, and has since then grown in number of components it hosts and provides. And it has a pretty large scope, as you can imagine, when you want to facilitate using EMF in web-based and cloud-based modeling tools. It has quite a large scope, ranging from middleware for making EMF models accessible to clients, which, for instance, also could involve adapters so that you can use or access EMF models via JSON and not only via XMI, which makes it easier in some cases when you hook up TypeScript-based clients, for instance, provide editing support and all that stuff. So there's a couple of components, the big scope and already a couple of components. Since this talk is too short to cover all components that are currently available in EMF.cloud, I will focus mostly on two of those components, one of which is the EMF Model Server, and the second one is the Eclipse GLSP, Graphical Language Server platform, which is essentially covering this use case where you have also diagrams that are not hooked up with a language server, textual language server, as Jan showed before, but really are hooked up with arbitrary EMF modeling backends. Right, there is quite a lot of things, so I will directly jump to the more technical slides and explain why we need those model server also in combination with GLSP. But I just want to mention, if you're interested, there is also a couple of other components. Like in EMF.cloud, we have also eCore tooling, so you can build eCore models in Theia or VSCode. There is also generic UI components like a tree model editor, where you have like a tree on the left-hand side, and depending on your selection, you get a form on the right-hand side to edit the model details, very similar to the generic EMF editor that you may know from Eclipse. And last but not least, alongside other components, there is an EMF JSON mapper based on Jackson, which allows you to load any EMF model in JSON and basically work with it the same way as you would work with it in XMI, but have JSON as the primary serialization format. Right, with that, I would like to jump to the first component that I would like to cover, which is the EMF Model Server. So first of all, the question is why we would use such a model server. So as mentioned before, our goal is to build web-based modeling tools that have all the great modern UI front ends in VS Code or in Theia, but still can use EMF on the server to benefit from all the greatness in the ecosystem that is available. Of course, you can use most of those technologies that come from EMF, like model management, serialization, commands, command stack, and all this stuff, because EMF has no dependency on a certain UI technology, and you can just do the same as you would do inside of Eclipse in rich client application, but do it on the server. However, this does not cover all the use cases that you would actually have in a typical modeling tool, because if you look at an example like this one, we have here a web-based modeling tool where we have a form-based editor with a tree master detail UI here. Then we have textual editor here and a graphical editor, for instance. And very typically, they all operate on a shared, quite large model. And parts of, for instance, this form-based editor would represent the part of the model highlighted here, and the graphical one an overlapping part, which is highlighted here, and so on and so forth. And now that's all no problem yet, but if you want to start modifying one editor, you would like to get these other editors updated as soon as you make a change. And to apply the architecture, the modern architecture, also that Jan mentioned before, we would like to employ on the server certain services that process those models so that they are optimized for the use for the respective representation. So for instance, for text-based languages, as Jan mentioned, for instance, we have the language server protocol, which is a perfect fit. So it sort of like encapsulates all the manipulation of text and the understanding of the language, and only provides to the editor what is really needed for the UI in order to provide good editing experience. And the same idea should be applied to all of these other editors, so that there are always services representation specific that fuel those editors with the respective know-how. So they encapsulate a little bit the know-how and also encapsulate the entire model. So of course, when we now want to synchronize those editors, since they operate on an overlapping part of the model potentially, they would have to be aware of each other, these services, but that's obviously not a very good architecture. This wouldn't scale if you have not 3, but like 10 of those services running. So we really don't want them to talk to each other, but still we want them to be synchronized when it comes to the model source. And this is exactly where the model server component comes into play. So it's really just a component that allows to synchronize a model instance across multiple services that require access to this model in order to provide certain editing capabilities. And I can also show this application in demo, in action, just a demo how this would look like. Let me just switch to this application and maximize it here. So we can, in this application, it's really just an example application that demonstrates how you can build such a modeling tool. So there is a diagram editor that I can open. There is a form-based editor that I can open alongside it. And then there is a textual DSL editor that I can also open. And as you can see here, those are all different types of editors, but they share the same, they talk to the same model in the back. So for instance, when I now add a new task here, we see that here this new task has been added as well. And when I change the name, for instance, we see that this name has also been changed here, and vice versa, of course. When I rename it here again, then the diagram will also update and show immediately what the respective label of this element is. And last but not least, here in this textual editor, which is based on Xtext, you have all the language support that we have seen already in the previous talk, but you can also access for instance, to refer to tasks of this joint model. And you can see here that it also is aware already of this new task that I've just created with the name text123 and so on. So basically, all these editors have certain services that provide the editing capabilities for the respective front ends, and those services talk to the same model server instance so that they can share a joint model. Let's have a look at how this is actually implemented. Basically, the model server is just a Java-based server based on Javelin, which is quite a nice REST framework. And the goal is to provide also the dirty state and the common command change interface to multiple services, so that you only need to load a model once and then can share the dirty state across all the services. So it's a little bit, if you're in Eclipse terminology, it's a little bit like a shared editing domain, and nothing more than that. So it purposefully is just focusing on this task. So it does not provide any model repository capabilities or versioning or anything like that. You can hook it up with existing technologies to the model server itself, but it doesn't try to solve all the problems, but really just focus on this one. In order to achieve that, it provides a REST API, as mentioned before, with the typical operations, and provides the model in multiple formats depending on the client what they prefer, either JSON or XML. And there is a client library for Java and JavaScript, so that it's very easy to hook up to this model server. So just to give you a very rough example how this may look like, in order to load a model in the Java API, you would just instantiate a new model server for a certain URL, and then you can request URIs, model URIs, and once they are loaded, you can process them in some way. And that's essentially what all these services that represent, for instance, the diagram editor capabilities as well as the textual editing, what they do is they obtain a certain model in the format that they would like. And with that, when they don't specify an additional flag, they all load the same instance in one session. Now you can subscribe via socket to changes. And also patch models using this model server. So for instance, you this editor can send with a very simple JSON format commands basically to this server, where you can specify, for instance, that here we have a command with the type add, and we add a new object value here at the index 1, for instance. And this this service would then send this to the server, this command. The server would perform it if it can. If it can't, then it would just reject and let the client know. But if it can, it would perform the actual model change and would then notify all listeners again so that they can synchronize and react to it. And that's exactly what we have seen here before in the when I showed that I renamed a certain element in the diagram, that the text that the the tree editor would be aware of it and could react to this change in some way. Yeah, so that's basically the model server that is provided in EMF.cloud. And just to give you also more context, let's have a look at how this then can be connected to a service, like in this case, the example, GLSP. So GLSP is short for Graphical Language Server Platform. And really the idea of that is that it applies the architectural pattern of the language server protocol for text, but to graphical modeling in order to achieve the same goals and characteristics that we all find very useful in the language server protocol. And that is that it allows to build web-based diagram clients independently of how the client technology is created, or is what the client technology is. It allows you to encapsulate the language know-how on the server, so that you don't have to encode the language server very much on the client, so that you can basically replace it more easily and have really a front end or a client that can really focus only on rendering and user interaction. The Graphical Language Server Platform, or GLSP, is also an Eclipse project. It is more or less part of the EMF.cloud ecosystem, but technically it already incubated into an own project, since there was a lot of interest in using it in different use cases. And we wanted to have it as an own project in the meantime. So it's there also since 1.5 years at Eclipse, and is really focusing on this providing diagram editors. And it can be, just as mentioned here, it can be hooked up to the model server, but also to arbitrary other model sources. So let's have a look at GLSP, how the separation of concern between client and server is currently set up. So basically, when you look at a typical editor, diagram editor, there are a couple of capabilities typically encapsulated or implemented in such an editor, ranging from diagram editing, editing tools, visual feedback, which already show certain editing rules, whether you are allowed to add an element, for instance, in this context, or to rename or create an edge between model elements in another context, and so on. Commands to really apply changes, and so on, edit transactions, live validations, and all this stuff. So there's a lot of capabilities. In order to draw the line in GLSP, we specified that everything that needs to be on the client and to provide good usability in terms of fast feedback and rendering runs on the client, which is then rendering, editing tools, and visual feedback. And everything else runs only on the server. So this is what really encapsulates the language know-how, like editing rules through to model management. Of course, certain elements on the client need to be aware of certain parts from the language know-how. So for instance, the visual feedback needs to be aware about certain aspects of the editing rules to, for instance, show the user directly whether an operation can be applied in a certain context or not. And for that, there is this protocol that sort of parameterizes the client so that the client can already show, for instance, that you cannot rename an element in this case for this value, for instance, and reject the change in a nice, graceful way. For building such diagram editors with diagram servers, the GLSP project provides basically 4 components. It's on the one hand side a Java-based standalone server implementation, then of course the protocol, the client framework, which is then providing the actual diagram editing and visual feedback, server communication, and so on. And last but not least, the IDE or tool platform integration, so you can integrate GLSP editors in Theia, VSCode, or in Eclipse. It's based on quite cool technologies. So the Java-based server, for instance, is based on LSP4j, which is an Eclipse project to build language servers actually, but it has a generic base to build any JSON RPC servers. And it is heavily built on especially the diagram, or only the diagram client framework is built on Sprotty, which Jan showed in the previous talk, which we use for rendering and also for the model transfer between client and server. So just to give you an idea of how this actually looks like in practice when you open a diagram, so the client would request a language server for a specific URI, for instance. The server would then the language server would then load from an arbitrary model source, can be a model server as mentioned before, but can be an arbitrary model source, an EMF model, or also JSON, whatever you like, and translate this into the S model that Jan mentioned before, which would then be sent back to the client. And then based on Sprotty, this S model would then be rendered, which means translated into SVG and then rendered in the browser. So once the user would then like to apply certain operations, the client does not know, since it doesn't have any language know-how per se, does not know which operations can actually be applied. So the client requests, for instance, a number of things, for instance, the tool palette actions, context menus, editing capabilities, and so on from the server. And depending on the request, it would then render certain UI elements, like it would render a tool palette, and so on, which shows all the things that can be, for instance, added in this context. Once then the client would trigger such a tool palette action, for instance, for creating a node, the client is not aware of what this actually means, but it would just send the create node action with the specific type ID and some context information like location to the server. And then the server can actually process this action by invoking a handler that would then manipulate the original model source and then regenerate the graph, just like in the first step where we translated the model source into a graph. Again, to update the model, send this to the client, which then can then re-render the diagram. So this scheme is also exactly as already mentioned, sort of like a unidirectional action or event circle. So whenever there is an action coming in, we don't change the diagram directly, but we modify the model source and then regenerate the diagram, which has a lot of advantages when it comes to making it basically more simple to manage the different states of diagram, model, coordinates information, and all the stuff that you have. And it allows more easily also to share those changes with other services that might be hooked up to the EMF model server. So I don't have too much time to go into too much code. I just wanted to mention that there is 2 examples online that you can look at, which serve 2 different means. So on the one hand side, there is this minimal example, which you see down here. So it's really just an editor that allows you to draw rectangles. And here is the relevant code that is shown to implement that. So it's really not a lot. You have the client-side rendering specification or configuration that also Jan mentioned. So it's exactly basic pure Sprotty code. It only specifies how certain element types or diagram types map to certain views. And on the right-hand side, you see the corresponding server module configuration, which is based on dependency injection, where you can configure the diagram, for instance, with things like which element types even exist in this diagram. So they correspond then to this node and graph here on the left-hand side. And you can configure operation handlers, like here, this minimal create node operation handler, which is sort of an operation handler to create a node. And this is exactly what is then automatically shown here on the left-hand side in the palette. And the last thing you minimally need to specify is where does the original model actually come from. So that's basically the specification of what the model source is. And this is here in the simplest form, a JSON file that you can just read and translate into a diagram. The second example is the workflow example, which I will demo also, which is a more sophisticated example showing all the different capabilities of GLSP. So from direct editing, validation, and contextual editing with auto-completion and all this stuff, copy-paste. So it shows all the different features that you can actually do. Of course, then the code is not as simple as this anymore, but I can show you later how the code then roughly looks like. And I hope that it's still quite manageable, even though there are a number of capabilities being implemented. Last but not least, and that's the last thing I want to mention before the demo. Of course, a diagram editor is fine, but typically for building modeling tools, you want to integrate those in tool platforms so that you can combine those editors with other capabilities of the tool. So GLSP allows you to integrate GLSP editors in Eclipse Theia, VSCode, and also even in rich client Eclipse applications. So let me just show you how that looks like. I will show you now different examples of exactly the same diagram server in the back, but different front ends. So first of all, let's start with here the Eclipse rich client application. So when I double click this element, this WF file, you see here this workflow example that I've mentioned before. So you can basically, as you would expect, you can create elements, you can connect them with edges, you can move them, zoom in, zoom out, you can even change, for instance, the labels and so on. And you can also, for instance, navigate to other files inside this same IDE. So for instance, here with this push task, there is some example that we've just built so that you can navigate to the documentation. And what this would then do, it would open a second text editor where search for the push heading and would directly jump to it, so that you can really integrate diagrams with other editors very nicely in Eclipse, but also, of course, in other editors. Right, the same can also be opened, of course, in VS Code. So let me just now switch to VS Code. It's the same language server again, and you can here right-click on Open Workflow Example. So we see it's exactly the same functionality. You can again create those different types of elements and connect them with each other, and even change here the labels and so on and so forth. Of course, this is also integrated with platform capabilities like theming. So when you, for instance, change here the color theme, then the diagram would update according to the preferences of the language theme, for instance. And last but not least, this is integrated also with Eclipse Theia. So now I'm opening a browser that points to an Eclipse Theia instance. And here again, I can open the diagram editor exactly the same and do all the same changes as mentioned before. Just because I didn't show it before, a few capabilities that Theia and GLSP can do. So for instance, you can do, let me just create a decision node here. You can do validation. So when you run the validator, the validation is obviously run on the server and just markers are then sent down to the client. And these markers are then, of course, also integrated with the Theia platform so that they also show up in the central problems view. Of of course, when you click on them, you would then jump through the elements. You have undo redo support. So I'm now hitting Control Z, Control Shift Z to show you that. And there is also some additional sophisticated features like, first of all, of course, you have label edit validation, but there is also this contextual editing support where you can, for instance, open here a direct editor task, and then it would allow you to do certain actions in a more efficient way, where it has auto completion and of course also validation. So if you do something wrong, it would show it directly. And all this stuff is again handled actually on the server, interpreted and then sent down to the client, and may then lead, for instance, to a change of the model. So I can here specify 35, and then this model change would actually be applied. Right, let me just go back to the slides to see if I forgot to mention integrations that we have. Yeah, so I think I've shown keyboard shortcuts, integration with other views and editors, navigation across diagrams and other editors, as mentioned before, problem markers. Yeah, and sure, of course, copy paste is also supported. So for instance, when I now click on these, I select now these 3 elements, hit Control C, and then I hit Control V, and then we see that we got those again, and I can add them as often as I like. Of course, here is the most interesting part of that is not that copy paste is actually working, but how all these features are implemented. Since we want to encapsulate the language know-how on the server, all these things involve the server in some way or another. Just to give you an example, navigation across editors. So when you resolve an element against the model, for instance, then of course there is a navigation action that will be sent to the server so that the server can actually resolve against some query against the model, and would then just send down to the client to which graphical element we should navigate. Problem markers, for instance, the validation of obviously runs on the server and would just send down the problem markers. And for copy paste, on copy, the client would ask the server, what is the information that you would like to put into the clipboard? This would be then sent down to the client. The client actually puts it into the clipboard, and on paste, the client would again send the clipboard content to the server so that you can do more sophisticated stuff. And many of you probably know that copy paste in diagrams is not such an easy thing to implement. So it's good that we have that integrated on the server. Right, last but not least, I think I'm not sure how much time I still have left, but I just wanted to mention a few other cool things that are going on in GLSP, but also in the broader EMF.cloud ecosystem. So on the one hand side, there is quite a nice commercial FBD editor being developed by a company which builds on top of GLSP and also other technologies in the EMF.cloud ecosystem. So you see here, you can build quite sophisticated, nice looking diagrams, which are then integrated with also property views, as well as with other textual languages that you may reference from your diagrams and vice versa. Here is a screenshot also of the eCore support in Eclipse Theia. So you see here that there is also an eCore diagram editor with property views, just as the one that you're used to inside of Eclipse. And last but not least, what I find also pretty cool is that there has been a project where the GLSP editors have been integrated with the debug adapter protocol to allow debugging diagrams essentially. So you can, using the generic debug UI in Theia or in VSCode, jump through your diagrams, and the editor would always highlight the element where you're currently in. It allows you to add breakpoints. It can show you the variables or the scope where you're currently in, and you can navigate into or step over and do all these typical debug operations. Right, with that, a few conclusions. So first of all, as you have seen, we are using Eclipse Brody as a rendering technology on the client, and we are very, very happy with that. It's extremely flexible, and it makes it very easy to provide very modern looking diagrams, which can then, based on GLSP, also be hooked up to EMF-based model servers or diagram servers to provide editors. We feel in the last projects that we did in the last couple of years or 1 or 2 years that EMF.cloud unlocks a very high reuse on the server. So if you have existing EMF-based tools, it's actually quite nice to migrate them to a web-based front end without having to rewrite everything from scratch. So there's actually a little bit of refactoring typically in the beginning of those projects to separate the UI from the model management and the language know-how, but then it's quite straightforward to actually migrate in an incremental way your Eclipse-based modeling tool to cloud-based IDE or to Theia or to VSCode. We are very, very happy with the modular language server-oriented architecture because it's extremely versatile. So you can combine arbitrarily the different services like a textual language server with graphical language server platform, with the model server, without the model server, whether it reads the information that the model from a database or from a file. So this is very modular, and you can basically configure it exactly the way you like to do, which is very, very flexible in my opinion. And last but not least, I think this is also showing very well that building a diagram editor, for instance, with GLSP does not imply any tool platform lock-ins. So you can still choose whether you essentially want to target in the end Theia, VSCode, or even Eclipse Rich Client, or all of them at the same time. And I think this is very future-proof because it opens up platform migration very easily in the future because there is no one-size-fits-all platform. I'm sure you will be addressing different platforms in the future. As Jan said, VSCode is very popular now. 5 years ago, it was maybe IntelliJ. So it's changing a lot, and you don't want to re-implement everything again and again, especially when it comes to the language know-how. Right, if you have any questions, feel free to ask me now or also contact me. So my email address is here. And please also make sure to check out our project pages at Eclipse and on GitHub. And we have also there chat support, forums, and all this stuff. And we are looking forward to learn more about your use cases and questions. Thanks.
Thanks a lot, Philip, for the excellent presentation. Do we have any questions that you would like to ask? Well, maybe I can start. So I was wondering, maybe you have mentioned that and I have missed it, but I kept wondering, how do you specify the graphical concrete syntax of the visual language that you are rendering and so on? Do you use some DSL of your own? Do you use something like Sirius, or do you do it programmatically?
No, it's all programmatically, and as I mentioned, the separation of concerns is really that the client is responsible for rendering, and that's basically it. And for that, we are using Sprotty. So basically, what Sprotty does is you have this S-graph, which I think I have sketched here, which consists of nodes and edges and labels and compartments and all this stuff, and each of them have a type. And you map those types in this configuration to view elements. And each view element is essentially reading this diagram element and translates it into SVG. So it's essentially what you do is you specify SVG to implement the rendering. That's for simple nodes where you, for instance, have only a rectangle with lines and so on and so forth. Of course, you can make compartments to nest them within each other. Then it gets a little bit more complex. So again, you have SVG for each of those components, but then you may have to apply layouters so that the inner structure of a diagram element is then layouted, for instance, with a flow layout, box layout, and so on and so forth.
Cool.
But yeah, we find this it depends really, of course, as always, on the use case. So if you have a DSL or like in Sirius, some sort of diagram model where you specify it, it's great for prototyping. You're very fast at a certain step, but at the same time, it also adds a layer on top of the whole rendering, right? So you need to sort of understand what this model means and how this interpreter would then actually render the model. And with Sprotty and GLSP, we are really going in more into the direction that we want to put an abstraction layer that is as thin as possible, so you can really very easily just specify SVG, and that's with that specify the rendering. And of course, it depends on the use case, but we feel it makes it, for instance, extremely simple to specify editors like this one here, where you have maybe also a little bit more complex shapes and ports and all this stuff, because essentially you are just translating a diagram abstract model into an SVG.
Gerson has a question. So maybe Gerson, if you could like to ask.
Yes, I have a question. Thank you for this very interesting presentation. So I'm just listening from Nantes in France. I was wondering if when you designed EMF.cloud, it was thinking to be a server, a kind of local server for local development, or also for distributed and concurrent environments.
Yeah, very good question. So at the moment, the EMF server, model server, is really meant to be used per user or per workspace. So when you have one user opening one workspace, you have one instance of the model server. It's not really meant to be like a collaboration repository where multiple users would connect to, at least at the moment. The main reason for that is we like to keep things very simple. And what we wanted to do is basically address exactly this problem to synchronize changes within one workspace or one application, synchronize changes between multiple widgets or diagram or whatever editors so that they can operate on the same model. In Eclipse, this is really simple, right? You just share the editing domain or the resource set, and then you basically get that for free. But in this more distributed environment that we have here, where we also want to have very modular services that are really focused on a specific diagram type or textual languages, we don't want to integrate them with each other, but we want them to share the same model state. And this is really the main target of model server. Whether at some point there is enough interest in the community to add such like really multi-user scenarios to the model server, I'm not sure. Maybe that's a good opportunity, but at the moment we are currently just focusing on this scenario.
Okay, thank you again for the presentation.
Thanks.
Davide, I think you also had a question.
Yeah, hi Philip, this is Davide. Thanks for your presentation. My question is related to the one from Gerson. So behind the model server, what's the plan in terms of the storage? Where the models that you are going to edit are really stored? I mean, there is any plan to support some, some remote repository where you store the models, where you load the model that you're going to, in order to open and modify. So what's the plan in this respect?
Right. So the plan is to be very, very agnostic about that. So in our products where we currently use the model server basically is just the resource set in a sense, the shared editing domain, and reads the model from arbitrary sources. Most of the time it would be XMI files or DSL files or whatever files you store your model in, and would then just load them from there. So basically what you can do there is you just use EMF as you would use it today with all the resource factories that you have available there. You can even use CDO if you like with the model server, because essentially the model server doesn't really care where the model comes from. It basically just needs to read the model somewhere, and you can override this part where you actually read the model. So you can actually hook up CDO if you like, or whatever model management platform that you would like to use.
Thank you.
The plan is, I think, to keep it like that. But of course, since it's an open source project, if there is enough interest to develop in one or the other direction, then you never know where the journey takes you, but that's at least the current plan.
Okay, thank you very much.
Thank you.
Right, so Lea Brunsby has another question, but her mic doesn't work, so I will ask for her. And she says, maybe I missed these points, but is it possible to generate XML files or JSON of your models? And is it possible to do cross-reference between different languages?
Yes, exactly. So yes, that's for sure possible. Maybe I was no, not maybe. I'm sure I was. I'm sure not wasn't very clear about that. So you can think of when you look at this picture, neither the diagram editor or the form-based editors really know the model or understand the model, and these services that add sort of like the representation-specific editing capabilities on top, they also don't really need to understand, for instance, how the model is serialized. So in the end, you have some component like the model server or whatever you want to write yourself that reads the model and would then provide it to the respective services, and they would translate it to the representation specific stuff. So you can store the models in whatever information or format you like. So maybe that's the first part of the question. And very typically, especially for GLSP, you don't have one model, but you have maybe multiple model sources like the semantic model and the diagram coordinate information and stuff like that. And you can just read both of them and translate them into the graph model to be then sent to the server. And for to answer the second question with cross-references and navigation, yeah, sure, that works without any issues. So I can maybe not show the perfect example, but I can show at least an example. So here we have just a very basic example where you can, I think it's called next, go to next node. So there is just a navigation to the next node. And what that does, it jumps to this next node here. What happens in the background is that the client, which doesn't understand the language whatsoever, just sends a navigation request action to the server and say, I have a navigation request for next, whatever that is. And the server would then resolve what the next element actually is, and would then send this back to the client. Of course, this is now in this simple case in the same diagram, but it can be in an arbitrary diagram. So if I, for instance, close this and don't save, and I click here, this is essentially also a navigation request coming from the outside. So if it would be two diagrams, it would just open the other element and so on. I hope that answered the question a little bit. Maybe just one last thing, there is also this I think it's called push. Yeah, you can open the example task with the at the task the example model with the task at the task push, and it would do it. And what this actually does, this is an opener configuration for the workflow file with a query name equals to push. And of course, the diagram client doesn't know anything about that, but it would send the query to the server in order to get it resolved, and then the server would send, you need to focus on this element with the ID, blah, 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 and this happens to be the push element.
Right. Felicien has another question. I can read it, or Felicien, you can ask it yourself. So he says, in EMF.cloud, is there a way to define node constraints?
Yes. So again, there is this constraints on multiple levels, I would say. So first of all, there is language constraints with respect to the meta model and additional constraints that you would have there. So this typically is more positioned here on this model management level, where you have the awareness of the full model. There you can do the model validation with additional constraints. Here there is currently a project going on also as part of the EMF.cloud project to add model validation to the model server. So this is work in progress, and I think already quite far. And then what would then happen is that the model server protocol, the API here, would be extended so that validation results can be sent, or that there are listeners for validation results, for instance, so that then these services can process them in any way. And I think it's important that these services can do that, because when you, for instance, change in this editor something that invalidates something that is shown in this editor, then the model would show a validation result. This would then notify the diagram server. Only the diagram server knows which graphical element is mapped to a certain number of elements in the backend model. So it would then know, okay, this element now needs to get an error marker, for instance. So this is the intended way of handling that. And then last but not least, I think the second level of editing constraints is editing constraints, where you want to restrict certain editing directly. And this is, for instance, can be implemented also in GLSP because the editor needs to be aware of it, right? So for instance, I'm allowed to create an edge from here to here, that's fine. But I'm not allowed to create an edge from a weighted edge from here to here. So basically this wouldn't show me do anything, right? But I'm allowed to add an edge from here to here, weighted edge. So there is certain editing rules that can be then sent down from the diagram server to the client, so that the client can handle it directly. There should be also visual feedback. I'm not sure why this isn't currently not working. So there should be a mouse marker showing that this isn't allowed. Not sure why it broke. I just compiled the development branch today, this morning. Maybe something broke.
All right. I said, well, there's another question. So I would suggest we have eaten most of the time that we have for the break and formal discussion. So I would suggest we make the last question and then we start. We have a 5-minute break. That's okay for everyone. So the last question would be from Benedict. And the question is, does EMF.cloud support model transformations or only the definition, manual editing, and validation of models?
Sorry, could you please repeat the last part so I understood it until transformation? What was the
rest?
Yeah,
does EMF.cloud support model transformation or only the definition, manual editing, and validation of models?
Mm-hmm. So the short answer is no, it does not support model transformation per se, because I think it would be blunt to try to solve that big problem in the model server. But it basically allows you to use anything EMF related or EMF compatible. So you can use whatever model transformation technology you like and hook it up in one way or another in the model server. So one example could, for instance, be that you want to load a model, then transform it into some other meta model before sending it, for instance, to a service like GLSP or whatever. So that can easily be done. You just have to write it with Java code in a sense that you need to invoke the model transformation, for instance, the ATL transformation from Java code there. But it doesn't provide any additional transformation support. But the rest you mentioned, like validation and so on, yes, that is part of, or should be part at some point of the model server.
Well, thanks a lot, Philip. It was an excellent talk and a lot of information that certainly will be very useful for us.
Thank you. I was very happy to be here, and thanks for the opportunity to talk about EMF Cloud.
Yeah, well, thanks to you.